Hi everyone, I hope this video finds you well. I wanted to give you some additional examples of piecewise functions. Basically just from my own experience, I know that it's a harder concept to kind of wrap your head around, especially in a 50-minute class time period. So piecewise functions, as I'll probably describe them in class, are kind of like the Frankensteins of functions. Basically because you're going to take pieces of functions and put them together to kind of create this newer visual. So I'm going to direct your attention to the first piece, and that's going to be x plus 1 if x is less than 1. So the information that you have located over here, so the if, so that conditional clause, this is actually referring to the domain that this particular piece of the function can exist on. So I'm going to use a green line here. We tend to not represent this line when we actually graph them, but for the time being, just as a learning experience, I'm going to go ahead and put this in. So if you notice between the two domains that have been provided for you, it looks like the dividing line is happening at when x is at 1. So I'm just going to, it's not quite an asymptote, but I'm just kind of going to say, here are where my two planes of existence are. My x plus 1 is going to live on this side of the green line, and my x cubed will live on this side of the green line. Okay? So I'm just going to clear those so you don't have to look at those and potentially get confused. But the next thing that I'm going to go ahead and do is I'm going to take my attention down over here, and I'm going to look at x plus 1. So this is a function, and for really quickly ask yourself, what kind of shape is this going to give you when you graph it? Or what kind of function does this look like? And hopefully you're saying, well, this looks like a linear function. So when I graph this, I should see a straight line. Well, what I'm going to go ahead and do is I'll create a table of values, and I'm going to start at 1, and then I'm just going to count backwards. And you probably don't need 4 points, but really just to drive it home that you will get a straight line, I'm going to go ahead and do that. And you don't necessarily have to use consecutive numbers either. You could have picked -5, you could have picked -10, anything along those lines, just so long as you have a couple points to help you draw it. So if I do f of 1, then I would get 1 plus 1. So my output value would be 2. F of 0, which is always a nice one to do since it's probably really quick math. You probably don't even have to actually write out that line. F of -1, that will result in 0. And then f of 2. And that's going to be 2 plus 1, which is 3. Some really hard math going on right now, right? So what I want you to know is how I'm going to plot these points. So I do have a point, that should be a -2, my fault. So that's going to change my answer, won't it? So this will become -1, my fault. So we have -2, -1. We have -1, 0. We have 0, 1. And as you can see with these extra points, you should kind of start seeing that straight line taking shape. So the last one at point 1, 2, I'm going to intentionally leave this as an open circle. The reason why is because of how the domain is written. Notice that it's less than 1. In other words, as we were discussing domain yesterday with inequalities, a less than sign means that you can get really close to the 1, but you can't actually use it. So this is an example of, here is my function for my line, getting really close, but not actually touching 1. Because, again, it would be really, really impossible to find the point, the x value that's right next to positive 1. So it's just easier to write an open circle over 1 and say, hey, my line is going to go there, and then it's going to get really close. Okay, so we've taken care of the first piece. Now let's move on to the second piece. And as you can see, here we have a cubic. So let's just say it's g of x is equal to x cubed. And think of the general shape that you have for a cubic. Hopefully by now you're starting to familiarize yourself with those, with our toolkit functions or our parent functions. And the general shape that it will take is something like this, where what is called the point of inflection actually happens at the origin. So basically, I have to start at 1 because that is where my domain starts. All right, and again, that's why I have that green line kind of dividing it down. Now I'm saying that my cubic function can start existing once we get to a domain of x is equal to 1 or bigger. So I'm going to use 1, 2, and 3. Okay. As you can probably note, this might be overkill. So if we do g of 1, we're going to put 1 cubed in. That will give me 1. G of 2, 2 cubed, or 8. And then g of 3, which is going to be 3 cubed, which is just going to be too big for our graph here, so we're only really going to focus on the first 2 points. So I do have a point at 1, 1, and note that I'm using a solid dot here because of the equal sign noted in the domain. Then I'm also going to do 2, 8, and I'm going to connect the two. And this is your piecewise function. As you can see, I'm going to try to highlight this. On the left-hand side of the green line, I have my linear shape. And then on the right-hand side, it's not as apparent, but I do have a piece of the cubic function graphed there. And the reason why I only have that piece is because I'm telling you in the very beginning that this cubic function can only exist when x is 1 or bigger. So I hope that example was helpful. If you do have any other questions, please let me know.